For today, we're going to review the Chapter 2.1 notes remotely, given the cold weather. I hope everyone's staying safe. Please, if you haven't already, take out your notes for for Chapter 2 and go to the beginning for Section 1. So categorical variables are a way of putting data into distinct categories or bins. I like to think about this as boxes. Each category represents a different box that we can sort observations into. So if we had a green box, we might put all of our green items there, a blue box, the blue items, a red box, the red items. This is different from continuous quantitative data because we're not really looking at how blue something is or how red something is. It simply is in the box or it isn't in the box. Once we've assigned a category for each observation, we can tally up how many observations fell into each box. So in this example, each of our ducks is an individual observation. We have 4 green, 6 blue, and 3 red. This is the way that we would answer how many are in each category when we're working with categorical data. We just tally up the counts. And so now take out your notes and we'll go through some definitions before we get into more examples. So the frequency is the number of times a data value occurs in a data set. I was referring to this as the count of observations before. A frequency table of a categorical variable provides a listing of the distinct values and their frequencies. So distinct values here means each of the different categories that are possible, and then the frequency with which they occur. A relative frequency table, and I'm skipping ahead just a little in the notes, so make sure you notice I'm going ahead a couple bullets. A relative frequency table of a categorical variable adds relative frequencies to the frequency table. So I've got an example here for you where we've got our relative frequency table laid out here. Now let's go through the definitions. Okay, so in a relative frequency table, each row represents the current box that you're counting for. So let's say if I was thinking about my ducks example, I would have a row for the category blue, a row for the category green, a row for the category red. The frequency is the number of observations counted in the current category. That was my count of ducks before. And the frequency adds up to the total number of observations in the data set. So everything should fall into one of the categories, and then this should all add up, except for in special cases. Relative frequency is equal to the frequency of the data value divided by the total observations in the data set. So if we were to put this back in our table, it would be relative frequency equal to frequency here over total observations. The percent is the relative frequency multiplied by 100. So these are mathematically very similar numbers. This is just taking this number here and multiplying it by 100. Your percent should always tally up to 100% when you have a simple categorical variable, and your relative frequency should always tally up to 1. When you're displaying categorical data like this, you might want to use tables and graphs. These are really good ways to share the categorical data. So let's go through, just for today, what it might look like for univariate data. That's data with just one categorical variable, like duck color. So here is a relative frequency table where we show the category, color of duck, the frequency, number of times each duck was counted, the relative frequency, taking that divided by the total number of ducks to create a proportion, and then the percent. Here is what it would look like if we did it as a graph instead. This is a frequency graph where each of these bars is as tall as the count, the frequency that we see here. So this is a really good way to do things. Let's go ahead and take a minute, pick out your notes, and fill in the frequencies, relative frequencies, and percents in the table about insurance type. Pause the video if you need time to work, and then start it back up when you're ready. So I've gone ahead and filled this in here. Our data set had observations just listed out with commas in between. So we had 5 private, we had 3 government, and we had 4 no insurance. Total of 12 observations in the full data set. I calculated the relative frequency using that 12 as the denominator, and then I took these numbers and converted them into a percent. Pretty straightforward. We just want to make sure that you get some practice. When you're showing these relative frequency tables, you actually don't need to show all the columns that I've been showing in the examples so far because it's redundant. Relative frequency and percent are essentially the same thing. It just depends on where you're putting the decimal point, whether you've multiplied by 100 or not. So by convention, when you're graphing things in class and when you're working on your own, you're going to either show the relative frequency or the percent, but usually not both at the same time. So now take out your notes again so we can write down this definition. A bar chart can visually show the frequency, relative frequency, or percent in each category. The proportion or height of bars relative to one another is going to look the same regardless of which of those three measures is used on the y-axis. So let's take a look and see what that means. So here is that frequency chart that you saw before, where each of these bars has a height equal to the frequency that we had observed in our duck count. Here's the relative frequency. So now each of these bars is as tall as the proportion that this represents of the sample, and here's the percent. And you can notice that these are essentially the exact same graph, just with different values on the y-axis. Because relative to each other, they all have the same height relationship. So which one you choose won't affect the looks so much as just how you talk about it and how you frame it. Okay, now we're going to move on to pie charts. These are circular graphs which denote the percentage of times a case takes a certain value out of all possible values of a variable. In these, a circle represents a whole. So here is a lovely bar chart with our data by color, as you saw before. And here's that same data represented in a pie chart. I do not like pie charts, and I say that they should be avoided in general. I'm not alone in this one. They are hard to interpret. They're confusing. The eye can't intuitively understand the relationship between these wedges in the same way that it can intuitively understand the relationship between these heights. They're generally hard to connect labels to. They're bad in many, many ways. That being said, you will probably see them often in the workplace, so that's why we make you learn about them. Please don't use them. If you do have to use them, they should only be used if the following conditions are met. The pie chart needs to be a whole pie. It has to display all possible categories. If you have observations that don't fall into one category, include a pie slice for anything that's missing or other. Every observation in the data set should be represented in only one category on the pie chart. So if you have an individual that you put into both a green and a blue category, that is not the right kind of data to be graphing like this. The goal is that 100% of the pie chart is showing 100% of the data and nothing is double counted. There are in your notes some additional guidelines on how to approach these. If you have to use them, make sure that you don't have wedges that are too small and just tread lightly. They can be helpful sometimes. Good luck. All right, so I'm going to pivot a little bit away from talking about the ways that we summarize these categorical variables and think about what we can do with the categorical variables. So categorical variables allow us to calculate the odds that something will happen. If we think about membership in a category, like being in a box, as a potential outcome, we can reframe categorical variables to calculate the odds of an observation falling in that specific category. So let's go back to our ducks example. We have these three boxes. We have ducks in each of the boxes. Let's say that we really wanted to drill in and focus on which of these ducks was blue. That's our outcome of interest, a blue duck. We can make a statement about the odds that we would get a blue duck by looking at how often we have blue ducks compared to how often we have anything other than a blue duck. So getting out your notes, odds give us a way to compare the proportion with a certain outcome to the proportion without the outcome. Odds are the ratio of a proportion with the outcome to the proportion without, and they can be used for retrospective, prospective, or cross-sectional studies. For odds, we're only concerned about one outcome of interest at a time. You would call it a success if something is in that category and a failure if it's anything else. So we really walk through things piecewise, only thinking about one thing at a time. So in our example before, the only thing that we're interested in when we're talking about the odds of blue ducks is whether they were blue. It does not matter what other color they were, simply that they weren't blue. When we're calculating odds, we take the relative proportion in a category and divide that by the proportion not in that category, so everything else. Mathematically, you can say 1 minus the proportion in that category. There are also other ways to do this if you ever want to learn different approaches, but that's the easiest way to think about it, is just, is it a success or is it anything other than a success? And because we know that success and failure should always add up to 1, you can just take 1 minus the proportion with the success to get the odds. When you interpret odds, you're thinking about how they relate to the number 1. So if, let's say, something happens as a success half the time and not a success half the time, that would then equal out to 0.5 over 1 minus 0.5 equals 1. So if something happens just as often as it doesn't happen, you're going to have an odds ratio, an odds of about 1. If something is less likely to happen, then that means that the frequency with which it happens is smaller than the frequency with which it doesn't happen. So it's less likely to happen. And if the odds are greater than 1, it's because this proportion is bigger than the proportion without happening. So let's go ahead and do an odds table for our ducks before. I have all of the colors of ducks here, but notice that for each one, I'm only focusing on one category at a time. So for green, I'm thinking about the 4 ducks that were green relative to all 13 ducks. For blue, the 6 ducks that were blue relative to all 13 ducks. And for red, 3 that were red relative to all ducks. If you remember, we were looking at success as blue ducks, then we should be focusing on this middle row here. And we can make a statement that the odds of success, the odds of having a blue duck in this sample are 0.8571. So just remember, if the odds are equal to 1, it's about as likely as not. Greater than 1, more likely to happen than not, and less than 1, less likely. So we could say that the odds of having a blue duck are 0.8571. It's less likely to happen than not, but it's close. You'll notice that this table looks a little bit different from how we presented our relative frequency table. Because we're looking at everything one row at a time, we don't do things laid out with the total at the bottom. We don't calculate relative frequency of everything together. Nothing would add up to 1 in an odds table. It's just a little bit different. Okay, now it's your turn. In Kentucky, 44% of households have elevated radon levels, which increases a person's risk for lung cancer. Let's calculate the odds that a household in Kentucky has elevated radon levels. Go ahead and get out your notes. And you don't have to do it this way, but I'm going to help you frame it up just in case it is useful for you. So I like to think about things with that table. We know that we have a proportion of 0.44, 44%. So I'm going to plug in that known value into this table here. Because the important thing in this equation is the proportion, we don't have to worry about back calculating frequencies or thinking about the households without radon. This number all by itself gives us everything that we need to calculate the odds. So go ahead and pause the video, take a minute, and calculate the odds using this known value. Okay, so to calculate those odds, you would take 0.44 over 1 minus 0.44, getting a total of 0.7857. So you can make a statement that the odds that a household in Kentucky has elevated radon levels are 0.7857. It's a little bit less likely than not. All right, your turn again. So in a sample of 250 smokers, 35 developed lung cancer. We want to know the odds that a smoker from this sample developed lung cancer. So once again, I'm going to help you get it framed up the way I like to think about it, but you can do it whatever way makes sense to you. Here, I only need to know about the number with lung cancer. I have those numbers here, so I have my total observations in the full data set, sample of 250 smokers. So I'm going to plug that number in here. I have the frequency in the category of interest, 35. So I'm going to plug that in here. Now the next thing I need to do is calculate the proportion in the category so that I'll have the information I need to calculate odds in the category. So we can just skip the no lung cancer for right now. Go ahead and pause the video, take a minute and do this and come back. Okay, so we were first tasked with calculating the proportion in the category, which is 35 over 250 or 0.14. Taking that 0.14 and plugging it into our odds formula, we get an odds of 0.14 over 1 minus 0.14 is 0.1628. So the odds that a smoker from this sample developed lung cancer are 0.1628. Fairly unlikely, but not that unlikely. So just to recap everything, when working with categorical variables, we want to know how many observations fall into each category. Once we assign observations to categories, we can make graphs, create summary tables, and calculate the odds of membership in each category. The important things that we covered today are how to present our categorical data with an example showing univariate graphs, graphs with just one categorical variable shown at a time. This is a relative frequency graph with the category variable on the x-axis and the relative frequency on the y-axis. We covered relative frequency tables where we summarize counts across categories, including the percentage or proportion of the total, helping us interpret the data and understand how these categories compare to each other. And we touched on odds, which let us compare the proportion with versus without a specific outcome. And for odds, just remember that the real reason we do these odds and the reason it's useful is that it helps us think about the chances for or against it happening. So whenever you're looking at odds, always remember you're thinking about, is it less than 1? Is it about 1? Or is it more than 1? Next time we connect, we'll cover rare events, which is when things have very unlikely chances and how we handle that in the math. Stay warm, stay safe. Thank you.